All right, we are looking at longest substring without repeating characters. This is our second sliding window problem, which we'll talk. We'll get a little bit more context on like what we mean by sliding window actually in today's problem. The last one we did, which is best time to buy and sell stock, it like is sliding window, but it's sort of, I don't know. I don't think it really embodies the algorithm super well. So today's is a great example of it. And if you're interested, we will be having our first in-person general body meeting tomorrow, and we'll actually talk a little bit about sliding window and about two-pointer and about interview skills and like tips and tricks and stuff like that. And we're gonna give away some gift cards. We got like $25 to Stereoscope Coffee. We got $25 to Canes because we love Canes in this household. I think we're gonna give away a year of Discord Nitro, like Nitro Basic, because that a year of actual Discord is or of actual Nitro is crazy. And I think we're gonna try and get donuts. So yeah, and you don't have to do anything. You can just show up and hang out with us, and you'll get a chance to win that raffle. Okay. Anyways, let's get to the problem. Let's take a look. So given a string s, we want to find the length of the longest substring without duplicate characters, which is exactly what it sounds like. So just to clarify what a substring is a contiguous, which, man, why'd they use that word? But a contiguous sequence of characters within a string. So contiguous just means all the letters have to be next to each other. So we can't have like spaces between the characters that we choose. Otherwise, this question would just be how many unique characters are there in the string, right? So we need them to be next to each other, and we need there to be no duplicate characters in the substring that we choose. Feels like a warm hug. I kind of agree with that. Contiguous does feel like a warm hug. It's a nice word. Okay, so let's look at an example just to see what we mean by this. So the first example here is zxy, zxyz, and the output is 3, which is the length of the longest substring that doesn't have any repeating characters. And there's actually a lot that we could choose here. Zxy has no duplicates, xyz has no duplicates, yzx has no duplicates. So any of those would have been valid substrings, but they all have length 3, so we return 3. And why is that the longest that we can get? Because any substring of length 4 here is going to have a duplicate. So like zxyz, for example, has a duplicate z, xyzx has a duplicate x, and hopefully hopefully it's obvious that these would not be good candidates. Okay, their next example is just 4 x's in a row, and the output is 1 because the longest string we can get that does not have any duplicates is just x, which has length 1. Yeah, so the premise, fairly straightforward here. The algorithm, we'll talk about it in a sec. So the constraints, the length of that string s is between 0 and 1000. So they didn't give us an empty string example here, but it's possible for us to get an empty string. And then s itself will consist of printable ASCII characters, which there was a question in the chat earlier about printable ASCII characters. This is really just to assure you that there will not be anything like specific. I think specifically what they're trying to call out here is like there is an unprintable ASCII character, which would make it really weird in terms of like looking at an example and being like, why is this the answer? You can imagine like if we had ASDF, but right in the middle is the unprintable ASCII character, we would go, oh, the answer is 4, but the answer might turn out to actually be 5. Anyway, so printable ASCII characters, so we're not dealing with anything weird here. It's just a bunch of individual characters. Yeah, okay, so let's talk about... Well, I don't think we'll code the naive solution for this because, frankly, it's weird and, like... Well, it's not weird. It's just kind of like it would be so slow that we wouldn't really want to submit it. But let's just talk about how we might handle this naively real quick. So I won't even copy over the whole string. Actually, we'll just do something like this. I don't know if that's what it was originally, but let's say this was our example string here. The naive solution might say, hey, let's actually try and make strings of every length possible. So in this case, the strings would be from length 0 to 1, 2, 3, 4, 5, 6, 7. I don't know why I had to count that. I should have known that. Okay, so we could say, hey, let's actually try and make all the string lengths from 0 to 7, or if we're being slightly smart about this, maybe we would say 7 to 0. And let's just see if we can find any strings that don't have any duplicates within, right? So we could say, hey, does the whole thing have no duplicates? Okay, in that case, then the length we should return is 7. But assuming we do find duplicates, which, how would we do that? We might have to do a 2-pointer approach if we didn't have knowledge about certain types of data structures that we'll use in the better solution. But we might say, hey, let's go ahead and run a pointer through, or we'll have like a pointer that goes through each character once, and then we'll compare it against every following character and see if we ever find duplicates. So for the 7 length, we would find it here and go, whoop, okay, we can stop considering 7 because there was a duplicate, right? And then we could say, okay, let's figure out how to get the 6 length characters or 6 length strings, which might be this, or they might be this, right? And we would continue this, and we would keep doing that until we got down to length 3, and then we would immediately find this string that had no duplicates and say, okay, there's our guy, right? Now that's not ideal because 1, it's a lot of different substrings to consider. And then 2, within each of those substrings, if we're not smart about it, we might have to do a significant amount of work. The actual amount of work is a little bit weird here because like the lengths shrink, and then that means the number of comparisons shrink. But this is certainly in the realm of like O of n squared, probably worse than that. It's probably closer to n cubed. It's somewhere in there because not only do we have to consider every sublength, but it's probably way worse than that, huh? There's some weird math involved here, but we would have to figure out like how many strings could we get by making selections of length 7, 6, 5, 4, 3, 2, 1. I don't know that off the top of my head. That's some weird statistic stuff. But anyways, hopefully it's clear that's way more comparisons than we really need to do. And one of the things that's making this really difficult for us is, well, I would say 2 things actually. The first one is we have to, or in our current way that we're solving this, we have to do this 2-pointer approach that requires us to do tons and tons of comparisons, right? Like in this one, we would do 6 comparisons, and then 5, and then 4, and then 3, and then 2, right? And not only would we do that, then we would do 6, 5, 4, 3, 2, 1, and then we would do 5, 4, 3, 2, 1, and 4, 3, 2, 1, and 3, 2, 1. And so it's all of these additional comparisons that are not really serving us well. And then the second thing is, like, surely there's a better way than just brute forcing our ways into considering all the possible lengths. Ideally, we'd like to have some smart way of determining, how can we just expand the length smartly, shall we say, until we get something that is very long and does not have duplicates. Okay, so here's the approach that we're going to take. Instead, we'll actually start from the beginning. And well, actually, let me use 2 different colors here. And we're going to form a window. And you're never going to guess, but the window is going to slide. It's kind of crazy. So what we mean by sliding window in this case, and I think this is pretty representative of sliding window problems as a whole, is we're going to widen this window so long as we meet the condition that is kind of set by the problem. So the window in this case is the stuff between red and blue, is how you might think of it. Okay, and so before we get into all the counter stuff and how we're going to store the data, the idea is, well, let's expand the window until we find a duplicate. And so basically we're going to keep expanding the window as long as the substring that we're looking at is valid. So this one's valid, this one's valid, this one's valid. As soon as it becomes invalid, we shrink the window from the other side until it becomes valid again. Okay, so valid window right here. We expand it one more time and it becomes invalid, so we move this over until it becomes valid again. Okay, and then we can repeat from the other side. So valid right now, invalid, slide it over, valid, or it was valid a second ago, now it's invalid, so we slide this over. Now this one's not like super interesting because like we just sort of keep sliding everything over one by one. But by doing this, at the very worst case, so let's say this was all x's, then the very worst case scenario is that we just do that over and over again. And even in that worst case scenario, so it's like, well, actually, let me start it over here. So they start in the same place. It goes valid, invalid, valid, invalid, valid, invalid, right? Even in this absolute worst case, we still only need to do 2 n comparisons, right? So the time complexity here is definitely O of n, right? We need to look over everything twice, but that's way better than looking over everything some like on the order of factorial times. So yeah, and that's, so the idea of the window is, and again, I think this is common for various other sliding window problems, is widen the window as long as you have something valid, and then shrink the window. Well, once you find something invalid, shrink the window until it becomes valid again. And you just continue to slide that window over. In this case, we'll know we're done by the time right reaches the end of the string, because if we found, like if we're already at this point and we've gotten that length recorded, when it moves over and we start shrinking it, there's no way for the answer to get bigger, right? So we can stop as soon as that blue pointer hits the end of the string. Okay, so here, let's address though the other issue, which was, hey, we keep having to make these comparisons to figure out if we have duplicates, right? Now that would worsen the time complexity greatly if we had to keep looking through and comparing everything against everything else and looking for duplicates that way. But if you were here when we started the Blind 75 and you learned a little bit about hash sets, hopefully you recall that hash sets are a great tool for us to figure out if we have duplicates or not. Because again, we hash the values and we can in constant time figure out if we've seen something or not before, as well as we can remove that thing very quickly in constant time. So what we'll do is we'll make a hash set that basically just stores all of the letters that are in the string right now at any given moment. So maybe we'll call this like scene. And when we start, we'll put that first letter in. So we'll say, hey, there's an X in the string right now. The way that we're going to determine validity, because we want to make sure there's no duplicates, is we'll slide the window over and say, hey, is this character in the scene set yet? And if it's not, then we're good. We can keep expanding, and we will go ahead and put it in and say, okay, now we've seen the letter Y, for example. And we'll do it again right here. So it's still valid. We check the scene, right? We look over here. We say, have we seen Z before? No, we haven't. So it's a valid string still. We'll put that in. And then the next time we slide over, we'll say, hey, have we seen an X before? And this time we have seen the X, right? So what we'll need to do is we'll need to shift over that left pointer until we no longer see that X, right? I guess, so to speak. And we'll change the example one more time in a sec to like demonstrate a more interesting version of this. But in this case, what happens is we go, oh, actually we have seen X before. Let's go ahead and, in whatever order we want, get rid of the X and also shift this over. And now we can check again, okay, is the new character that the new character that we're about to add, is that in the set? It's not anymore, so we're good, and now we can put it back in, because this time we do see the X, but it's over here now. Okay, so we can improve the comparisons part of this, or the duplicates part of this, by using the hash set, which I should mark that this is a set, by the way. Okay, so that's not, again, this example isn't super like exciting because we keep shifting over by one, but let's say instead the example was like, oh man, actually I'm struggling to come up with an example where it's better than this. Okay, actually no, it's pretty straightforward. Let's say instead we had like X, Y, Z, and then we had like A, and then Z. Let's say this was, I'm like, do I need more than that? Okay, so let's say this was the string we were looking at instead. Wow. GoodNotes used to, if you had like a filled shape like this and you erased, it would get rid of the fill. Congratulations, GoodNotes, on improving that. I love that. Okay. Anyways, so let's say this was the string we were looking at. Here's where this kind of becomes more powerful for us. So we would go through this, right? We would say, hey, we've seen X. No problems so far. We've seen Y. We've seen Z. It continues to be valid at each of these steps. We've seen A. And then as soon as we get here and it becomes invalid, we need to, again, move that left pointer over until we have a valid string again, right? Or a valid, really valid indexes that tell us what substring to use, okay? Now, in the previous problem, or in the previous version of this that we did, it shifted over by 1 and we immediately solved the problem. But here's the issue. Just shifting that over by 1 is not necessarily going to remove the duplicates, right? In this case, for example, the duplicate's actually in the middle of the string. So we'll have to slide this over. We'll get rid of the X, right? Ooh, let me shift the eraser here. Okay, so we say, okay, I got to shift the left pointer over. Let me get rid of the character that was there. Okay, are there still duplicates? Yes, there are, so I've got to get rid of the next character as well. Okay, are there still duplicates? Yes, there are. This is actually the last time there will be duplicates. We shift over. And now finally, we're at a position where we have a valid string. We can add the Z from that right pointer index, and then we keep moving. And one of the cool things about this is as we, like, between loops, so to speak, or between, like, complete windows, we're guaranteed that there are no duplicates, which means we only have to do this once. Like, we only have to get rid of the current duplicate. Because in the last loop, we would have gotten rid of the duplicates as well, and the last loop before that, and the last loop before that. So the nice thing about this is, between loops, we know that there's no duplicates, which means we just have to solve one duplicate issue, if that makes sense. Okay, I just talked so much. I should have paused for questions earlier, but I didn't. But here we are now. Any questions? Sid, I'm glad this is making sense, because that, yeah, the window is a nice visual. Well, we'll get on over to the coding. The code's actually not super complex for this, but I'm so glad. I'm so glad you can see it clearly. It's a good one. I like that. Okay, let's get on over the code. If anybody does have questions, I would love to answer them. Or if you have comments, etc., let me know. But let's get on over to the code. Okay, so core of the problem here. Yeah, well, you missed the whole explanation, but I'll re-go over it as we talk about the code. Welcome in, everyone who just joined. So again, we're going to have these left and right pointers. We actually have some options about how to initialize these. I'm going to say like 0 and 0, purely because one of the possibilities is we could have a length 0 string. Actually, let me think about this. Well, you know what? We'll set it to 0, 1. Well, okay, sorry. Here's what I'm thinking about as I'm, like, debating about this. We do need to, like, start by saying, oh, we've seen the first character of the string, right? Because otherwise we don't, like, where would we put it, I guess? If that makes sense. Well, I think this will make more sense in a sec. I'm going to say 0, 1, but because it's possible for us to have a 0 length substring, or 0 length string, I'll also say, hey, if the length of the string off the bat is 0, go ahead and just return 0. Because if there's nothing in it, we can't have a length of more than 0 anyways. Okay, so I'll initialize these pointers left and right. And this is our window right here. Okay, and then we're going to need that set, which I'm going to call scene. And I'm going to go ahead and put sleft into it, just because this forms a basis for us to say, like, have we seen this character before? Yeah, so, like, for example, if the first 2 letters are X, then we can catch, ooh, the first letter was X. That means we got to slide the left pointer over, right? Okay. I don't think we've used this syntax before either. So this just means make a set and put sleft into it. So pretty straightforward there. Okay, and then now what we need to do, again, our loop condition is while right is length, then the... What did I just say? While right is length... While right is length... While right is less than the length of S. So as long as right is, like, at a valid index of the string, what do we need to do? Again, the first thing is, have we seen this letter before, right? Actually, is it? Let me think. Yeah, so, well, okay, hold on. Yeah. So say while s right is in scene. So if this character that we're currently looking at is one that we've already seen earlier in the... Oh, you know what? Actually, hold on. Oh, no, yeah, we're good. If this is something we've already seen, then what do we need to do? Well, we need to move left over by 1. But before we do that, we need to remove it from the scene set. So scene.remove s left, and then left plus equals 1. So this is basically just saying, like, move the left pointer over, and as you do that, go ahead and remove that letter from the scene set, because it's not quote-unquote in the string anymore, right? Okay, we're going to continue doing that as long as the right pointer letter is in that scene set, but as soon as it's not in there anymore, we know that we can add it and still have a valid substring. So at this point, we can say scene.add s right. And then at this point, since we have a valid string, we can say, okay, maybe this is the longest string we've seen so far. And actually, that's one thing that I'm missing right now, is like a current max, which I'll initialize to... I'll initialize it to 1, actually, because we started with these at 0 and 1. So we know that there's at least a length of 1. Okay. Okay, so we add in the right character to the scene set, and then now we can see if we've got a higher max than before. So whatever is bigger between the current max and right minus left plus 1. Because, for example, if our indices are 0 and 3, that's actually length 4, right? So subtract them and then add 1 gives you the length of the string. Okay, and that, I think, does it, actually. I love that my one comment is just sliding window. Ivy jumped in, and I was like, I have to make sure I comment this one well, and then I didn't, so I'm so sorry. But let's see if we can get some more explanatory comments in here. I just feel like there's not much to say. I don't know. We can just clarify here. Like, we don't need to wait for left to get to end, because that can only shrink the substring. Okay, so that's like a good clarifying comment that says, hey, I made this decision. Here's the rationale for it, right? It's not reiterating what's already in the code. It's just saying, here's the reason for it, in case you were wondering, or here's why we don't need to, continue looping after that. Okay, so while s right in scene, again, this is like one of those, like, I don't need to write, like, if we've seen this letter before, because that's what this means, right? So this is a good example of self-documenting code here. Yeah, this has to come after because we have to remove it first. There's not much else to say here. I think that's it, and then we'll return current max. Oh, and then we have to move right over at some point. So since we're not using a for loop, we have to kind of manually do that. Yeah. This does feel kind of backwards, though, now that I'm looking at it. Maybe we should have done this, and then this, and then this. So this doesn't matter. This would have worked either way. I'm just thinking, like, in terms of the logic of the problem, it does kind of make more sense to do this. Like, we're going to move right over and see if we can make this work. Oh, wait, no, actually, this isn't great because, wait, is this going to fuck with right is less than length s? Yeah, because this is going to give us index problems. We could do this, but I think I like it better how it was before. So we'll leave it like this, and then just see if we can flip it around later. Okay, I think this is it. I think we don't need really comments for these parts. So let's take a look and see if it runs. Yippee! And yippee! Okay, let's see though if I can swap that around. I think it'll still work just fine. If we do this and then we do that, I think it's the same thing. Like move right over and then we can evaluate if it's a good candidate or not. Does that work? I don't know. I don't feel like... Okay, never mind. Yeah, well, anyways, we got a version that worked. I'm sure we could figure out a way to increment right earlier, but it works out the other way, so we'll leave it as it is. Yeah, I agree. Well, I guess it would... Yeah, anyways. It definitely worked the way we wrote it the first time, and it's in line with the way that we described it. I just feel a little bit bad about this. Like, I feel like there should be a way to initialize them both to 0 and then figure it out from there. And we could probably figure it out, but I'm kind of tired, so we're going to call it there, y'all. Just a reminder, if you're planning on tuning in tomorrow, we're going to do this session at 6 p.m. because we have our general body meeting, which, again, I know a lot of you guys were here for this earlier, but we're going to give away some gift cards. We're going to have donuts, I think. We're going to talk about interviewing and how you can do really well at that, because we want you to do really well at that, and then be like, Leet Club helped me so much, or whatever. Anyways, and we'll do another sliding window problem tomorrow, but it'll be at 6 p.m. I think we're going to do it like live in the room, but we'll also stream it. So like whether you're online or in person, I'll still see you at 6 p.m. in HSD. I don't know the room number. It's somewhere in there. It's somewhere in the server. Go find it. You're smart people. Go find it. Anyways, have a good night. HSD 113. I'm getting the news. HSD 113. Wow, thank you guys. And I think that's it. Sweet. Thanks for tuning in, y'all. And I'll see you tomorrow.